So here's something worth thinking about as you settle in tonight. Right now, somewhere on this planet, there are about 440 nuclear reactors running. They're humming along in France and Japan and the United States and dozens of other countries, splitting atoms apart trillions upon trillions of times every second, and that silent, invisible process is keeping the lights on for something like 1/10 of the world's electricity. You've probably never heard one. You've probably never seen one up close. But the odds are pretty good that some of the energy flowing through the wires in your walls right now started as a uranium atom that was torn in half. And the story of how we figured out that trick, how we went from not even knowing atoms existed to building machines that could break them apart and harvest the energy inside. That story is one of the strangest, most dramatic, most consequential things that ever happened. So let's start at the beginning, the real beginning, and let's take our time with it. The first thing you need to know is that for almost all of human history, nobody had any idea that atoms were real. I mean, the ancient Greeks kicked the idea around. Democritus, around 400 BC or so, suggested that if you kept cutting matter into smaller and smaller pieces, eventually you'd reach something that couldn't be cut anymore, and he called that thing atomos, meaning uncuttable. It was a beautiful guess, but it was just philosophy. Nobody could prove it. Nobody could test it. And for about 2,000 years, the idea mostly just sat there gathering dust while people argued about other things. It wasn't until the early 1800s that the atom started to become a real scientific concept, something you could do chemistry with. John Dalton, an English school teacher. And I love that about this story, that so many of the people who changed everything were not grand professors, but quiet, slightly obsessive individuals working in modest circumstances. Dalton proposed in 1803 that each chemical element was made of identical atoms with a specific weight, and that chemical reactions were just atoms rearranging themselves. He couldn't see them. Nobody could. But the math worked. The patterns in how chemicals combined made sense if you assumed these tiny, indivisible particles were real. And for most of the 19th century, that was the picture. Atoms were the smallest thing. They were solid little balls, like tiny billiard balls, and that was that. But here's the thing. Nature is always more interesting than our models of it. And starting in the 1890s, a series of discoveries began to crack open the atom and reveal that there was a whole hidden world inside it, a world with more energy locked away than anyone could have imagined. The first crack came in 1895 from a German physicist named Wilhelm Röntgen. He was working with cathode ray tubes. These are just glass tubes with most of the air pumped out, and when you run electricity through them, they produce a glow. Lots of physicists were playing with these tubes at the time. But Röntgen noticed something strange. He had covered his tube with black cardboard, and yet a fluorescent screen sitting nearby was glowing. Something was coming out of that tube, passing through the cardboard and hitting the screen. He had no idea what it was, so he called them X-rays, X for unknown. And within weeks, he had taken the first X-ray photograph, an image of his wife's hand showing her bones and her wedding ring, and the world went absolutely wild. It was front-page news everywhere. People were stunned. Here was an invisible ray that could pass through solid matter. The atom, it seemed, was not as simple as everyone thought. Now, Röntgen's discovery didn't directly lead to nuclear power, but it set off a chain reaction. And I mean that metaphorically, though we'll get to the literal kind soon enough. Because his discovery inspired other scientists to start hunting for mysterious rays, And one of those scientists was a French physicist named Henri Becquerel. Becquerel was interested in phosphorescence, materials that glow after being exposed to light. He wondered if phosphorescent materials might also emit X-rays. So in early 1896, he took some uranium salts, which were known to phosphoresce, and he placed them on top of a photographic plate wrapped in dark paper. His idea was simple: expose the uranium to sunlight to make it phosphoresce, then see if it fogged the photographic plate through the paper, which would suggest X-rays were being emitted. And it worked. The plate was fogged. Becquerel thought he'd proven his hypothesis. But then, and this is one of those wonderful accidents in science, the weather in Paris turned cloudy. For several days, he couldn't do his experiment because there wasn't enough sunlight. So he stuck the uranium salts and the wrapped photographic plate in a drawer and waited. When he finally developed the plate, expecting to see maybe a faint image from whatever residual phosphorescence was left, the image was just as strong as before, maybe stronger. The uranium was fogging the plate all on its own, without any sunlight, without any external energy source at all. It was just radiating something, continuously, from within itself. Think about what that means for a second. Here was a material that was spontaneously, endlessly giving off some kind of energy, and nobody had asked it to. Nobody had heated it up or shone light on it or done anything to it. It was just sitting in a dark drawer, emitting invisible rays, all by itself. Where was that energy coming from? Becquerel didn't know. Nobody knew. But the question was now out there, hanging in the air, and it would take decades to fully answer. The energy was coming from inside the atom, from the nucleus, from a place nobody even knew existed yet. And this is where Marie Curie enters the story, and honestly, her life is one of those stories that's almost too dramatic to be real. Maria Sklodowska was born in Warsaw in 1867, when Poland was under Russian occupation. She was brilliant, driven, and deeply stubborn in the best possible way. Women couldn't attend university in Poland at the time, so she worked as a governess to save money, then moved to Paris in 1891 to study physics at the Sorbonne. She lived in a tiny sixth-floor apartment, sometimes so cold in winter that the water in her wash basin froze overnight. She barely ate. She studied relentlessly, and she was one of the best students in the entire university. She married Pierre Curie in 1895. Pierre was already a respected physicist, and their partnership became one of the most productive collaborations in the history of science. When Marie learned about Becquerel's mysterious uranium rays, she decided to make them the subject of her doctoral research. And her first major insight was deceptively simple but profound. She measured the rays coming from various uranium compounds and realized that the intensity of the radiation depended only on the amount of uranium present, not on what chemical compound it was in, not on temperature, not on any external condition. This meant the radiation was coming from the uranium atoms themselves. It was an atomic property. She coined the term radioactivity to describe it. And then she found something strange. Some of the uranium ore she was testing, a mineral called pitchblende, was more radioactive than pure uranium. That shouldn't have been possible if uranium was the only radioactive element. Something else was in there, something even more radioactive. So she and Pierre set to work isolating it, and this is where the story gets physically grueling. They were working in a converted shed, basically an abandoned dissecting room at the School of Physics, with no proper ventilation, no real lab equipment. They processed tons of pitchblende by hand. Marie would spend entire days stirring boiling, caustic solutions in enormous vats with an iron rod. then carefully separating out fractions, testing each one for radioactivity. It was backbreaking, dangerous work, and it went on for years. But in 1898, they announced the discovery of not one, but two new elements. The first they named polonium, after Marie's beloved homeland. The second they named radium, and radium was extraordinary. It was millions of times more radioactive than uranium. It glowed in the dark, a faint, eerie blue-green light. It was warm to the touch, measurably warmer than its surroundings, because it was releasing so much energy from within itself. Pierre once strapped a vial of radium salts to his arm for 10 hours and documented the burn it left on his skin. They were handling the most radioactive material anyone had ever encountered, and they had almost no understanding of the danger. Here's what's remarkable about this moment in history. Radioactivity was clearly releasing enormous amounts of energy, but nobody understood where it was coming from. The atom was supposed to be a solid, indivisible thing. How could it be pouring out energy like this, apparently forever? Some scientists worried it violated the conservation of energy. Others speculated that atoms were somehow absorbing energy from their environment and re-emitting it. The truth was stranger and more wonderful than any of them guessed. Meanwhile, across the English Channel, a New Zealander working in England was about to blow the atom wide open. Ernest Rutherford was one of those people who seemed to have been put on Earth specifically to figure things out. He was big, loud, confident, and had an almost supernatural intuition for experimental physics. He'd come to Cambridge from New Zealand on a scholarship in 1895, and by the early 1900s, he was already one of the leading figures in the new science of radioactivity. Rutherford figured out that radioactive materials emit at least two different kinds of radiation, which he named alpha and beta. Alpha particles were heavy, positively charged, and relatively slow. Beta particles were lighter, negatively charged, and faster. A third type, gamma rays, was identified soon after. These were pure electromagnetic energy, like X-rays, but even more penetrating. And Rutherford realized that when an atom emits an alpha or beta particle, it actually transforms into a different element. This was transmutation, the old dream of the alchemists, turning one element into another. It was real. It was happening all the time, in every speck of radioactive material on Earth. Atoms weren't permanent. They could change. They could decay. But the real bombshell, and I use that word knowing what's coming later in this story, came in 1911, when Rutherford and his colleagues Hans Geiger and Ernest Marsden performed one of the most famous experiments in the history of physics. They fired alpha particles at a thin sheet of gold foil and watched where the particles went. Most of them sailed straight through, which was expected, the prevailing model of the atom at the time, proposed by J.J. Thomson, imagined it as a diffuse blob of positive charge with electrons embedded in it, like plums in a pudding. Alpha particles should zip right through something like that. But some of the alpha particles bounced back. Not many, about 1 in 8,000, but some came back at sharp angles, and a few bounced almost straight back toward the source. Rutherford later said it was as if you fired a 15-inch artillery shell at a piece of tissue paper, and it came back and hit you. It was, he said, the most incredible event of his life. What it meant was that almost all the mass of an atom and all of its positive charge was concentrated in an incredibly tiny, incredibly dense core. The nucleus. The atom was mostly empty space, a vast emptiness with a tiny, heavy center and electrons orbiting far away. If you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a marble sitting on the 50-yard line. But that marble would contain almost all the mass, and it was held together by forces that were, pound for pound, millions of times stronger than any chemical bond. That's the key insight. That's the seed of everything that comes next. The nucleus of an atom is bound together by an almost incomprehensibly powerful force, and if you could find a way to release even a fraction of that binding energy, the amount of power you'd unleash would dwarf anything chemistry could offer. A single kilogram of uranium, fully fissioned, releases roughly the same energy as burning about 2,700 tons of coal. Think about that ratio. 1 kilogram versus 2,700 tons. The energy was there, locked inside the nucleus, waiting. The question was whether anyone could figure out how to get it out. And that question was about to become very urgent, because it was the 1930s now. The world was sliding toward war, and a quiet, meticulous German chemist named Otto Hahn was working late in his Berlin laboratory on an experiment that was about to change everything. Hahn wasn't alone in that lab, and the person beside him matters enormously to this story. Her name was Lise Meitner, and she was one of the most brilliant physicists of the 20th century, an Austrian woman who had clawed her way into the male-dominated world of German physics through sheer, stubborn brilliance. She and Hahn had been collaborators for over 30 years. They were a remarkable team. Hahn, the chemist, meticulous at separating and identifying elements, and Meitner, the physicist, the one who understood what the atoms were actually doing. They complemented each other perfectly, but by late 1938, Meitner was gone. She was Jewish by birth, and as the Nazi regime tightened its grip, she'd been forced to flee Germany that summer, escaping across the border to the Netherlands with little more than a small suitcase and 10 marks in her pocket. She ended up in Sweden, isolated, working in a borrowed lab, but still exchanging letters with Hahn almost constantly. And it was through those letters that one of the most consequential discoveries in human history unfolded. Here's what Hahn was doing. He was bombarding uranium atoms with neutrons. This was a technique that had been pioneered a few years earlier by the Italian physicist Enrico Fermi, who we'll come back to because he becomes central to this whole story. Fermi had discovered that if you fired neutrons at various elements, you could create new, heavier elements. The neutron would be absorbed into the nucleus, and the atom would transform into something else. Fermi had worked his way up the periodic table, element by element, and when he got to uranium, the heaviest naturally occurring element, he expected to create brand new elements heavier than uranium. Transuranic elements, elements that didn't exist in nature. And he thought he had. He announced the discovery of new elements, and it made headlines. But something wasn't quite right. The results were messy. Other labs tried to replicate the work and got confusing results. Nobody could cleanly identify what was actually being produced when you hit uranium with neutrons. So Hahn took it on. He was, after all, one of the best radiochemists in the world. If anyone could sort out the chemical mess, it was him. And in December of 1938, working with his assistant Fritz Strassmann, Hahn carefully analyzed the products of neutron-bombarded uranium and found something that made no sense. Among the debris, he found barium. Now, barium has an atomic number of 56. Uranium has an atomic number of 92. You don't get barium by chipping a little piece off uranium. Barium is roughly half the size of uranium. It was as if you'd thrown a pebble at a boulder and the boulder had split clean in two. Hahn was baffled. He was a chemist, not a physicist, and he didn't have a theoretical framework for what he was seeing. So he wrote to Meitner. And this is where the story gets beautiful, in a quiet, human way. It was Christmas, 1938. Meitner was visiting friends in the small Swedish town of Kungälv, near Gothenburg. Her nephew, Otto Robert Frisch, who was also a physicist, had come to visit her. Frisch was working in Copenhagen with Niels Bohr at the time, and he'd come to spend the holidays with his aunt. When he arrived, he found her poring over Hans' letter, deeply troubled by what it said. Frisch wanted to go cross-country skiing. Meitner wanted to talk about barium. So they did both. Frisch on his skis, Meitner walking briskly beside him in the snow, and together they worked out what was happening. Meitner knew something crucial. She knew about the liquid drop model of the nucleus, an idea that Bohr had been developing. The model treated the nucleus like a drop of liquid, held together by surface tension, which in nuclear terms was the strong nuclear force. But uranium was the heaviest natural element, and its nucleus contained 92 protons, all positively charged, all repelling each other. The strong force held them together, but just barely. The nucleus was already under tremendous internal stress, like a water droplet that's been stretched almost to the point of breaking. And Meitner realized that when a neutron entered this already strained nucleus, it could provide just enough extra energy to cause the whole thing to wobble, elongate, and split apart. Not chip, not crack, split. Into two roughly equal pieces, plus a few leftover neutrons. She and Frisch sat down. Well, she sat and he probably toweled off, and they did the calculation. They used Einstein's famous equation, E equals mc squared, the one from 1905 that everyone knows, but few people truly feel the weight of. Here's what it says. In plain terms, mass and energy are the same thing, and the exchange rate between them is enormous. The speed of light squared is about 90 billion in standard units, so even a tiny amount of mass, converted to energy, yields a staggering amount. Meitner calculated the mass of the two fragment nuclei, the barium and the krypton, roughly, and compared it to the mass of the original uranium nucleus. The fragments, together, weighed slightly less than the original. Not by much, a tiny fraction of a percent. But when she plugged that missing mass into Einstein's equation, the energy it corresponded to was about 200 million electron volts per atom. Per single atom. That was roughly 10 times more energy than any nuclear reaction anyone had seen before, and millions of times more than any chemical reaction. The numbers worked. The physics worked. The uranium nucleus was splitting in two, and it was releasing a breathtaking amount of energy when it did. Frisch rushed back to Copenhagen and told Bohr, who reportedly slapped his own forehead and said something like, "Oh, what fools we've been. We should have seen this before." Frisch needed a name for the process. He talked to a biologist friend and borrowed a term from cell biology. The way a living cell divides was called binary fission. So Frisch called this nuclear fission, and the name stuck. Now let's slow down for a second, because I want you to really feel what just happened here. For 40 years, since Becquerel noticed his photographic plates fogging, scientists had been probing the atom, peeling back layer after layer, and they'd accumulated an enormous understanding of its structure. But fission was different. Fission wasn't just another discovery about how atoms behave. It was the discovery that you could break a heavy atom apart and release energy on a scale that had no precedent in human experience. And there was something else. Something that made the discovery not just remarkable, but terrifying. Remember those leftover neutrons? When a uranium nucleus splits, it doesn't just produce two smaller nuclei in energy. It also kicks out 2 or 3 free neutrons, and those neutrons can go on to hit other uranium nuclei, which split, and release more neutrons, which hit more nuclei. You see where this is going. A chain reaction. The possibility of a self-sustaining chain reaction, where one fission event triggers the next, which triggers the next, in an exponential cascade, was recognized almost immediately. And it was recognized in January of 1939, with the world on the brink of the most destructive war in human history. The timing could not have been worse, or, depending on your perspective, it could not have been more consequential. Bohr brought the news to America. He arrived in New York on January 16, 1939, and within days, physicists across the country were replicating the fission experiment. It wasn't hard. You needed a neutron source and some uranium, and you could see the energy bursts on your instruments. Unmistakable, enormous. Labs at Columbia, Johns Hopkins, the Carnegie Institution, they all confirmed it within weeks. The physics community was electrified and also deeply unsettled because everyone understood the implication. If you could sustain a chain reaction in uranium, you could build a weapon of almost unimaginable power. And if you could build one, so could Germany, the country where fission had been discovered, the country that still had Otto Hahn and Werner Heisenberg and some of the best physicists in the world. This is where Enrico Fermi comes back into the picture, and he deserves a proper introduction because he's going to be at the center of this story for a while. Fermi was Italian, born in Rome in 1901, and he was one of those rare physicists who was equally brilliant at theory and experiment. Most physicists lean one way or the other. They're either blackboard people or lab people. Fermi was both. He had an almost supernatural intuition for physics. His colleagues called him the Pope because he was considered infallible. He'd won the Nobel Prize in 1938 for his neutron bombardment work, the same work that had started the whole chain of events leading to fission. And when he went to Stockholm to collect the prize, he didn't go back to Italy. His wife Laura was Jewish. Mussolini's fascist government had adopted anti-Semitic laws, and Fermi took his family straight from Stockholm to New York. He joined the physics department at Columbia University in January 1939, just as the fission news broke. So here you had Fermi, arguably the best experimental physicist alive, sitting in New York City, fully aware that uranium fission was real, fully aware that a chain reaction might be possible, and fully aware that the Nazis might be pursuing the same idea. The question was no longer theoretical. It was practical, and it was urgent. Could you actually build a controlled, self-sustaining nuclear chain reaction? And what would it take? The answer wasn't simple, because there was a catch. Natural uranium is a mixture of two main isotopes, uranium-238, which makes up about 99.3%, and uranium-235, which makes up only about 0.7%. And here's the thing. It's uranium-235 that fissions easily when struck by a slow-moving neutron. Uranium-238 tends to just absorb the neutron without splitting, swallowing it up like a sponge and going quiet. So if you wanted a chain reaction in natural uranium, you had a problem. Most of your uranium was the wrong kind. The neutrons released by fission were fast, and fast neutrons were more likely to be absorbed uselessly by uranium-238 than to cause another fission in the rare uranium-235. You needed to slow the neutrons down, moderate them, in physics terminology, so they'd be more likely to trigger fission in U-235 before U-238 could gobble them up. This is where the concept of a moderator becomes essential, and it's one of those engineering details that sounds dry until you realize it's literally the difference between a chain reaction that sustains itself and one that fizzles out. A moderator is a material that slows neutrons down without absorbing too many of them. You need something with light atoms, because when a neutron collides with a light atom, it transfers more of its kinetic energy. the same way a billiard ball slows down more when it hits another billiard ball than when it hits a bowling ball. The best candidates were ordinary water, heavy water. That's water made with deuterium, a heavier isotope of hydrogen, and graphite, which is pure carbon. Each had trade-offs. Ordinary water was great at slowing neutrons, but absorbed a few too many. Heavy water was nearly perfect, but incredibly rare and expensive. Graphite was good enough, available in quantity and relatively cheap, but it had to be extraordinarily pure. Even tiny traces of impurities like boron would absorb neutrons and kill the reaction. Fermi chose graphite, and in 1940, working at Columbia with a small team, he began building the first experimental piles, layers of uranium and graphite stacked together, carefully arranged so that neutrons born from fission in one uranium lump would be slowed by the surrounding graphite and wander into another uranium lump, causing another fission. Each experiment was bigger than the last, and each one got closer to the critical threshold, the point where the chain reaction would become self-sustaining. But they weren't there yet. They needed more uranium, purer graphite, and a bigger pile. And by 1941, with America now in the war after Pearl Harbor, the resources and the urgency were finally about to converge. The Manhattan Project, as it would come to be known, changed everything, not just for Fermi, but for the entire trajectory of nuclear science, and honestly, for the trajectory of the 20th century itself. Now, the Manhattan Project is one of those stories that's been told so many times it can start to feel like myth. But let's slow down and really look at what happened, because the engineering details are extraordinary, and the human stories behind them are even more so. In the summer of 1942, the U.S. Army Corps of Engineers established a new district office in Manhattan. That's where the name came from, nothing more dramatic than a bureaucratic address, and placed the entire American nuclear effort under military control. The man put in charge was Brigadier General Leslie Groves, a career Army engineer who had just finished overseeing the construction of the Pentagon, which at the time was the largest office building in the world. Groves was blunt, demanding, impatient, and supremely organized. He was not a scientist. He was a builder. And that turned out to be exactly what the project needed, because the fundamental challenge in late 1942 wasn't really a physics problem anymore. The physics was understood well, enough. The challenge was engineering on a scale nobody had ever attempted. But before any of that could ramp up, Fermi still had to prove the basic concept worked. He had to demonstrate in a real physical experiment that a self-sustaining nuclear chain reaction was possible. And this is where the story moves to Chicago. Fermi's team had relocated from Columbia to the University of Chicago as part of a consolidation effort called the Metallurgical Laboratory, the Met Lab, everyone called it. And there, underneath the west stands of Stagg Field, an old football stadium the university no longer used for games, Fermi began constructing what would become Chicago Pile 1. Just think about that setting for a moment. A disused squash court beneath the bleachers of a football stadium in the middle of a major American city. That's where humanity first sustained a nuclear chain reaction. There was no containment building, no radiation shielding to speak of, no emergency cooling system. By modern standards, it was breathtakingly reckless. But Fermi had done the calculations, and he trusted them. He knew exactly how much reactivity the pile would produce, and he was confident it could be controlled. The pile itself was an elegant brute force structure. Imagine a flattened sphere, an oblate ellipsoid, roughly 25 feet wide and 20 feet tall, made of about 45,000 graphite blocks. many of them with holes drilled to hold lumps of uranium metal or uranium oxide. The whole thing weighed close to 400 tons. The graphite served as the moderator, slowing the neutrons. The uranium was the fuel, and threaded through the pile were cadmium control rods, strips of cadmium metal that could be slid in or pulled out. Cadmium is a voracious neutron absorber. With the rods fully inserted, they'd soak up so many neutrons that no chain reaction could develop. Pull them out gradually, and you'd let more and more neutrons survive to cause fissions, creeping closer and closer to criticality. On December 2nd, 1942, Fermi's team gathered for the final experiment. There were about 49 people present, standing on the balcony of the squash court, watching. Fermi directed the withdrawal of the control rods one step at a time, checking his instruments after each adjustment. He had a slide rule, just a slide rule and his own calculations, and he'd predict what the neutron count should be at each step, then compare it to the actual reading. Every time, his prediction matched. The man's intuition for neutron physics was almost uncanny. By early afternoon, the last control rod was withdrawn to the calculated critical position, and the neutron counters began to climb, not in a burst, but in a steady, exponential rise. The chain reaction was self-sustaining. It ran for about 28 minutes at a power level of roughly half a watt, barely enough to light a flashlight bulb, before Fermi ordered the control rods reinserted. Arthur Compton, the physicist overseeing the Met Lab, made a famous coded phone call to James Conant at Harvard. "The Italian navigator has landed in the New World," Compton said. Conant asked, "How are the natives?" Compton replied, "Very friendly." And that was it. That was how the news of humanity's first controlled nuclear chain reaction was communicated. No press release, no fanfare. Wartime secrecy wrapped the whole thing in silence. Now here's what I want you to appreciate about this moment, because it's easy to rush past it. What Fermi demonstrated wasn't just that chain reactions were possible. He demonstrated that they were controllable. That you could start one, sustain it at a chosen power level, and shut it down. That distinction is everything. It's the entire foundation of nuclear power as an energy source. A bomb is an uncontrolled chain reaction. You want it to multiply as fast as possible before the whole thing blows apart. A reactor is a controlled chain reaction. You want it to hover right at that critical threshold, producing a steady output of heat. And the engineering principles Fermi established that afternoon in Chicago, using a moderator to manage neutron speeds, using control rods to fine-tune reactivity, monitoring neutron flux to know exactly what the pile is doing. Those principles are still the bones of every nuclear reactor operating today. The technology has gotten vastly more sophisticated, but the fundamental logic hasn't changed. Of course, the immediate purpose of Chicago Pile 1 wasn't to generate electricity. Nobody was thinking about power plants yet. The purpose was to prove the concept so the Manhattan Project could move on to its real goals, which were twofold. First, build a uranium bomb. Second, build a plutonium bomb. And this is where the engineering gets truly staggering in scale. Let's talk about the uranium path first, because the problem it presented was one of the most daunting industrial challenges anyone had ever faced. You remember the isotope issue? Natural uranium is about 99.3% U-238 and only 0.7% U-235. And it's the U-235 that fissions easily with slow neutrons. For a bomb, you needed highly enriched uranium, stuff that was mostly U-235. But here's the thing about isotopes. They're chemically identical. You can't separate them with any chemical process. They're the same element. They have the same electrons, the same chemical bonds, the same reactions. The only difference is mass. U-235 has 3 fewer neutrons than U-238, making it about 1.3% lighter. That's it. That tiny mass difference was the only handle you had to grab onto, and you had to use it to separate one isotope from another on an industrial scale, producing kilograms of nearly pure U-235 from tons and tons of natural uranium. Multiple approaches were pursued simultaneously because nobody knew which one would work best, and there wasn't time to try them sequentially. Gaseous diffusion was one. You convert uranium into a gas, uranium hexafluoride, and push it through barriers with microscopic pores. The lighter, U-235 molecules diffuse through the barrier slightly faster than the heavier U-238 molecules, but the enrichment per stage is minuscule, so you need thousands of stages in series, each one feeding into the next, in enormous cascading plants. The facility built for this at Oak Ridge, Tennessee, the K-25 plant, was, when completed, the largest building in the world under one roof. It was U-shaped, half a mile long, and it consumed more electricity than some entire states. Electromagnetic separation was another approach, Ernest Lawrence's idea, based on his cyclotron work at Berkeley. You ionize uranium atoms, accelerate them through a magnetic field, and the lighter U-235 ions curve on a slightly tighter radius than the heavier U-238 ions, so they land in different collectors. It worked, but it was painfully slow and inefficient. The calutrons, that's what they called the separation units, required enormous magnets, and there wasn't enough copper for the windings. So the project borrowed 14,000 tons of silver from the U.S. Treasury. Actual silver from Fort Knox, wound into electromagnetic coils. The Treasury officials were apparently horrified. And then there was thermal diffusion and centrifuge methods that were explored and mostly set aside for the time being. The point is, the Manhattan Project threw everything at this problem, spending billions of dollars in 1940s money, and employing tens of thousands of workers, most of whom had no idea what they were actually making. The secrecy was extraordinary. Workers at Oak Ridge knew they were doing something important for the war, but the compartmentalization meant that a person operating one stage of the gaseous diffusion cascade might have no idea what the substance was or what the overall purpose of the plant was. Now, the plutonium path was a completely different engineering challenge, and in some ways even more remarkable. Plutonium doesn't exist in nature, or rather, it exists in such vanishingly small quantities that it might as well not. But Fermi's chain reaction had shown the way to make it. When U-238 absorbs a neutron, it doesn't fission. But it does become U-239, which is unstable. It undergoes beta decay, turning into Neptunium-239, which then decays again into Plutonium-239. And Plutonium-239 is fissile. It splits readily, just like U-235. So if you run a reactor with natural uranium fuel, the U-238 that's sitting there doing nothing useful from a fission standpoint is actually slowly transmuting into plutonium. You're breeding new fuel inside the reactor. To get the plutonium out, you dissolve the spent fuel rods in acid and use chemical separation, because plutonium is a different element from uranium, so chemistry works just fine. But to produce enough plutonium for a bomb, you needed big reactors running at high power, and you needed a chemical separation plant to extract the plutonium from intensely radioactive spent fuel. This is what was built at Hanford, in the remote desert of eastern Washington state. The Hanford site eventually housed 3 full-scale production reactors cooled by water drawn from the Columbia River, along with massive chemical processing canyons, buildings so radioactive inside that all operations had to be done by remote control behind thick concrete walls. The engineering of those separation canyons was pioneering work in what we'd now call remote handling and hot cell technology. Nobody had ever dealt with materials this radioactive on this scale before. They were inventing the procedures as they went. The whole Manhattan Project, when you step back and look at it, was really 3 or 4 separate industrial revolutions happening simultaneously, all in secret, all under wartime pressure. And the human cost of that pressure was real. Workers at Hanford and Oak Ridge were exposed to radiation levels that we'd consider completely unacceptable today. Safety standards were primitive. The understanding of long-term radiation effects was incomplete. People got sick. Some of those health consequences wouldn't become apparent for years or decades. But by the summer of 1945, the project had succeeded in both paths. The uranium bomb, called Little Boy, used a simple gun-type design. One subcritical mass of U-235 was fired into another to create a supercritical assembly. The plutonium bomb, called Fat Man, used a far more complex implosion design because plutonium's properties made the gun-type approach unworkable. The implosion design required shaping explosive charges around a plutonium core with extraordinary precision, so that the detonation wave would compress the core uniformly from all directions. This was the work of the Los Alamos Laboratory in New Mexico, directed by J. Robert Oppenheimer, and the story of that laboratory, the personalities, the arguments, the all-night work sessions in the desert, is one of the great human dramas of the 20th century. But we'll come back to Oppenheimer. What I want you to hold on to right now is this. By August 1945, when those 2 bombs were dropped on Hiroshima and Nagasaki, the world had seen what nuclear energy could do in its most terrifying form. The war ended, and almost immediately, a new question arose. A question that had been simmering in the background the entire time, even during the Manhattan Project, even among the scientists building the bombs. The question was simple and enormous. Could this same energy, this same chain reaction, be harnessed not for destruction, but for something useful? Could you take the heat from a controlled reactor and use it to boil water, spin a turbine, and generate electricity? Could nuclear fission power cities instead of destroying them? The answer obviously was yes. But getting from yes in principle to yes in practice turned out to be its own epic engineering journey, full of competing designs, political battles, spectacular ambitions, and quiet disasters that nobody outside a small circle of engineers ever heard about. And that journey, from bomb to power plant, is what we're settling into now. So picture the world in 1946. The war is over. The atomic bomb has changed everything: geopolitics, military strategy, the public imagination. But here's what's easy to forget. At this point, there are exactly 0 nuclear power plants anywhere on Earth. Not 1 watt of electricity has ever been generated by nuclear fission for civilian use. The reactors that exist, Fermi's old Chicago pile, the production reactors at Hanford, they were never designed to make electricity. They were designed to make plutonium, or to prove that a chain reaction was possible. The heat they produced was literally waste. At Hanford, the cooling water that carried away the reactor's heat was just dumped back into the Columbia River. Nobody was capturing that energy. It was an afterthought. But some people had been thinking about it. Even during the Manhattan Project, scientists like Enrico Fermi and Eugene Wigner and Alvin Weinberg had sketched ideas for reactors that could do useful work. Weinberg, in particular, and he's someone worth remembering because he'll keep showing up in this story. Weinberg was a young physicist at the Met Lab in Chicago, and he was already thinking past the war, already imagining a world where reactors powered cities and desalinated seawater and propelled ships. He was a true believer in the peaceful atom, and he spent the next 4 decades trying to make that vision real. But in 1946, all of that was still theoretical. The first real question was institutional. Who would control nuclear energy in peacetime? During the war, it had been the Army, General Groves and the Manhattan Engineer District. But now Congress had to decide, does the military keep control, or does it pass to civilian authority? This might sound like a bureaucratic detail, but it shaped everything that came after. The answer came with the Atomic Energy Act of 1946, which created the Atomic Energy Commission, the AEC, and placed nuclear energy under civilian control. The AEC took over all the Manhattan Project facilities, all the research, all the fissile material. The military still had a huge stake, obviously, because nuclear weapons remained central to national defense. But the AEC was a civilian agency, and its mandate explicitly included developing peaceful uses of atomic energy. That mattered. It meant that reactor research wasn't just a side project, it was an official national priority. Now, the AEC inherited a problem. They had reactors that made plutonium, and they had a lot of very smart scientists, but they didn't have a clear path to a power-producing reactor. And here's the thing. There wasn't just one way to build a reactor. There were dozens of possible combinations. Think about it. You have to choose your fuel, natural uranium, enriched uranium, maybe even plutonium or thorium. You have to choose your moderator, graphite, regular water, heavy water, maybe beryllium. You have to choose your coolant, the substance that carries the heat away from the reactor core. And that could be water, gas, liquid metal, maybe even molten salt. Each combination has different physics, different engineering challenges, different advantages. And in the late 1940s, nobody really knew which combination would work best. So the AEC funded a whole portfolio of reactor experiments, scattered across the national laboratories. But the design that ended up winning, at least in the United States, at least for the first generation, came from an unexpected direction. It came from the Navy. And this is where we meet one of the most consequential and controversial figures in the entire history of nuclear power, Hyman G. Rickover. If you've never heard of Rickover, that's okay. He's not as famous as Oppenheimer or Fermi. But in terms of shaping the nuclear industry as it actually exists today, he might be more important than either of them. Rickover was a Navy captain, later an admiral, and he was, by all accounts, one of the most difficult, demanding, abrasive, brilliant, and effective leaders the U.S. military has ever produced. He was the son of Jewish immigrants from Poland. He grew up in Chicago, went to the Naval Academy, and spent years as an engineering officer on submarines and surface ships. He was not a physicist. He was an engineer through and through, and his engineering philosophy was simple and unyielding. Things must work. They must work reliably. They must work safely. And if you tell him something can't be done, you'd better have an extremely good reason, because he will make you explain it to him in detail, and then he will probably tell you to do it anyway. In 1946, Rickover was assigned to Oak Ridge, Tennessee, to study nuclear technology. He quickly became obsessed with the idea of a nuclear-powered submarine. And think about why that's such a compelling application. A conventional submarine of that era ran on diesel engines on the surface and electric batteries when submerged. The batteries had limited capacity. A submarine could only stay underwater for a day or two at most before it had to surface to recharge. That made submarines vulnerable. A nuclear reactor, though, a reactor doesn't need air. It doesn't need oxygen to burn fuel. A nuclear-powered submarine could stay submerged for weeks, even months. It could cross entire oceans without surfacing. It would be, in military terms, a revolution. Rickover lobbied relentlessly for a naval reactor program. He was not a man who took no for an answer. He maneuvered himself into a unique dual position. He reported to both the Navy's Bureau of Ships and the AEC simultaneously, which gave him bureaucratic leverage that nobody else had, and he assembled a team of engineers at a facility called the Bettis Atomic Power Laboratory, run by Westinghouse near Pittsburgh. Their job was to design, build, and test a reactor that could fit inside a submarine hull, produce enough power to drive the ship, and, this was non-negotiable for Rickover, be safe and reliable enough that you could trust it with a crew of young sailors living right next to it for months at a time. The design they settled on was the pressurized water reactor, the PWR. And here's how it works, because this design is still the most common type of nuclear power plant in the world today, so it's worth understanding. You start with the reactor core, fuel rods made of enriched uranium, arranged in a careful geometry with control rods that can be inserted or withdrawn to regulate the chain reaction. Surrounding the fuel is ordinary water, regular light water, H2O. Now this water serves two purposes simultaneously. First, it's the moderator. It slows down the fast neutrons produced by fission so they can be captured by other uranium-235 nuclei and keep the chain reaction going. Remember how we talked about Fermi using graphite as a moderator back in Chicago? Same principle, different material. Water works as a moderator because hydrogen atoms are almost the same mass as neutrons, so when a neutron bounces off a hydrogen nucleus, it loses a lot of its kinetic energy, like a billiard ball hitting another billiard ball. Very efficient. Second, the water is also the coolant. It absorbs the heat generated by fission and carries it away from the core. But here's the clever part, and this is what makes it a pressurized water reactor. The water in the core is kept under very high pressure, around 150 atmospheres or so. At that pressure, water doesn't boil even at temperatures well above its normal boiling point. You can heat it to over 300 degrees Celsius and it stays liquid. Why do you want to keep it liquid? Because if it boiled inside the core, the steam bubbles would change the moderation properties, and controlling the reactor would become much more complicated. So you keep the primary water under pressure, circulate it through the core where it gets extremely hot, and then send it through a device called a steam generator, basically a big heat exchanger, where the hot, pressurized primary water transfers its heat to a separate loop of water that's at lower pressure. That secondary water boils, produces steam, and the steam spins a turbine connected to a generator. In a submarine, the turbine drives the propeller shaft. In a power plant, it drives an electrical generator. But the basic principle is the same. And here's a feature of the pressurized water reactor that Rickover loved. It has a natural safety characteristic. If the reactor starts to overheat and the water temperature rises, the water becomes less dense, which means it becomes a less effective moderator, which means fewer neutrons are slowed down enough to cause fission, which means the chain reaction naturally slows down. The reactor has a built-in tendency to stabilize itself. Engineers call this a negative temperature coefficient of reactivity, and it's one of those elegant things where the physics itself acts as a safety mechanism. It doesn't make the reactor foolproof. Nothing is foolproof, but it provides a fundamental layer of self-regulation that Rickover found deeply reassuring. The prototype reactor for the submarine program was built not in a submarine, but in the Idaho desert at a facility called the National Reactor Testing Station, now the Idaho National Laboratory. They actually constructed a complete submarine hull section buried partway in the ground and installed the reactor inside it so they could test the entire propulsion system under realistic conditions. This prototype, called the S-1W, or sometimes just the Mark I, first achieved criticality in March 1953. And it worked. It worked beautifully. The reactor produced sustained power, the steam plant operated reliably, and Rickover's team proved that a pressurized water reactor could drive a submarine. The first actual nuclear-powered submarine, the USS Nautilus, was launched in January 1954 and commissioned in September of that year. Its performance was staggering. In 1958, the Nautilus made the first submerged transit of the North Pole, traveling under the Arctic ice cap, a voyage that would have been utterly impossible for a conventional submarine. Rickover's vision had been vindicated, and the pressurized water reactor had proven itself in the most demanding environment imaginable. But here's what matters for our story about power plants. The success of the naval reactor program had a massive and in some ways distorting effect on the civilian nuclear industry. Because Rickover's PWR worked so well, and because Westinghouse had developed all this expertise building naval reactors, the pressurized water reactor became the default choice when the United States started building commercial nuclear power plants. There's a phrase that historians of technology use, path dependence, and it applies perfectly here. The PWR wasn't necessarily the best possible design for generating electricity on land. It was the best design for fitting inside a submarine. Those are different engineering problems. A submarine needs a compact, high-power density reactor that uses highly enriched uranium fuel. A land-based power plant has plenty of space, doesn't need to be compact, and would benefit from using less enriched fuel. But the PWR had a head start. The engineering was proven. The supply chain existed. The expertise was there. And so the PWR became the dominant reactor type in the United States, and eventually in much of the world. Meanwhile, though, other designs were being explored, and some of them were genuinely fascinating. At Argonne National Laboratory near Chicago, a physicist named Walter Zinn, who had been one of Fermi's colleagues on the Manhattan Project, was working on a different kind of reactor entirely. In December 1951, Zinn's team achieved something remarkable at a facility in Idaho called EBR-1, the Experimental Breeder Reactor. It was the first reactor in history to generate usable electricity from nuclear fission. The amount was tiny, enough to light 4 200-watt light bulbs, but the symbolism was enormous. And the breeder part of the name points to something even more interesting, because EBR-1 wasn't just producing energy. It was designed to create more fissile material than it consumed by converting non-fissile uranium-238 into plutonium-239 through neutron capture. The breeder reactor concept was, in the early 1950s, considered the ultimate future of nuclear power because it promised to multiply the world's effective fuel supply by a factor of 60 or more. Instead of using only the rare U-235, which makes up less than 1% of natural uranium, you could eventually burn through all that abundant U-238 as well. But the breeder reactor story is complicated, and it winds through decades of hope and frustration and political controversy. We'll come back to it. What I want you to notice right now is that in the early 1950s, The field was wide open. Multiple reactor concepts were being tested simultaneously, and nobody knew which ones would win out. You had Rickover's pressurized water reactor, already proven in a submarine. You had Zinn's breeder concept, promising to stretch fuel supplies almost indefinitely. You had the British, who were building gas-cooled reactors using graphite as a moderator and carbon dioxide as a coolant. The Canadians were developing heavy water reactors, the CANDU design, which could run on natural uranium without any enrichment at all. And scattered across the American national laboratories, there were even more exotic ideas: molten salt reactors, sodium-cooled reactors, organic-cooled reactors, even reactors that used homogeneous fuel dissolved directly in water. It was a period of extraordinary creativity, and it's worth pausing here to appreciate just how open the question still was. Because the reactor type that would come to dominate the world hadn't been chosen by some grand committee weighing all the options. It was chosen, in large part, by momentum. Here's how it happened. In 1953, President Eisenhower gave his famous Atoms for Peace speech at the United Nations. And this speech matters enormously because it reframed nuclear energy in the public imagination. Up until that point, the atom was associated almost entirely with weapons, with Hiroshima, with the arms race, with the terrifying prospect of thermonuclear war. Eisenhower wanted to change that narrative. He proposed that the nuclear nations of the world should contribute fissile material to an international agency, which would then help develop peaceful applications, power plants, medical isotopes, agricultural research. The speech was partly genuine idealism and partly Cold War strategy, because the United States wanted to position itself as the benevolent leader of the atomic age, in contrast to the Soviet Union. But whatever the motivation, the effect was transformative. Suddenly, civilian nuclear power wasn't just a laboratory curiosity. It was a national priority, backed by presidential prestige and federal dollars. The Atomic Energy Commission, under this new mandate, moved quickly. And the design they chose to scale up first for a full commercial demonstration was, you guessed it, the pressurized water reactor. Not because it was necessarily the best design for generating electricity on land, but because it was the design they knew. Rickover's team had already built one. Westinghouse had the engineering expertise. The Navy had proven the concept worked reliably under the most demanding conditions imaginable. So when the AEC partnered with the Duquesne Light Company to build the first full-scale nuclear power plant in the United States, at a place called Shippingport, Pennsylvania, they went with a PWR. The reactor was essentially a scaled-up version of the submarine reactor, adapted for stationary power generation. It reached criticality on December 2nd, 1957, exactly 15 years to the day after Fermi's Chicago Pile 1. That date was no coincidence. Someone had a sense of history. Shippingport was modest by later standards, about 60 megawatts of electrical output, enough to power maybe 25,000 homes. But it worked. It fed electricity into the grid. It demonstrated that nuclear fission could be harnessed not just for weapons or submarine propulsion, but for the mundane, essential task of keeping the lights on. And it set the template. Over the next decade and a half, the American nuclear industry would build dozens of reactors, and the vast majority would be pressurized water reactors, or their close cousin, the boiling water reactor. Let's talk about that cousin for a second, because the boiling water reactor, the BWR, is an interesting variation. In a pressurized water reactor, remember, the water in the reactor core is kept under such enormous pressure that it can't boil, even at temperatures well above 300 degrees Celsius. That superheated water then transfers its heat through a steam generator to a separate secondary loop where the water does boil and drives the turbines. It's a two-loop system. The boiling water reactor simplifies this. In a BWR, the water in the reactor core is allowed to boil directly. Steam forms right there among the fuel rods, rises to the top of the reactor vessel, and goes straight to the turbine. One loop instead of two. Fewer components. Simpler plumbing. General Electric became the main champion of the BWR design, and it became the second most common reactor type in the world. Now, you might be thinking, if the water is boiling right there in the core, and that steam is going directly to the turbine, doesn't that mean the turbine and all its associated piping become slightly radioactive? And yes, that's exactly right. The steam picks up small amounts of radioactive contamination from the reactor core, which means the turbine hall in a BWR plant has to be treated as a mildly radioactive area. Workers need dosimetry badges, and maintenance is a bit more complicated. In a PWR, the secondary loop is clean. The steam that hits the turbine has never touched the reactor core, so the turbine building is essentially non-radioactive. That's one of the trade-offs. The BWR is simpler in some ways, but introduces this contamination issue. The PWR is more complex, but keeps the radioactive water contained in a smaller, more manageable primary loop. Both designs work. Both are safe when properly operated. And together, they account for something like 85% of all the nuclear reactors operating in the world today. But here's what's really interesting about this period. The late 1950s through the 1960s. Nuclear power went from being an experimental curiosity to a commercial juggernaut with astonishing speed, and the optimism was almost intoxicating. There's a famous phrase from that era, "too cheap to meter," which is often attributed to Lewis Strauss, the chairman of the Atomic Energy Commission, in a 1954 speech. The idea was that nuclear electricity would eventually be so abundant and so inexpensive that it wouldn't even be worth measuring individual household consumption. You just pay a flat fee, the way you might pay for water in some cities. Now, whether Strauss was actually talking about fission reactors or about the even more speculative prospect of fusion is debated by historians. But the phrase captured the mood. People genuinely believed that nuclear energy was going to transform civilization. Electricity would become essentially free. Deserts would bloom with desalinated seawater. Ships and planes and even cars might run on atomic power. And for a while, the trajectory seemed to support that optimism. In 1963, Jersey Central Power and Light ordered a reactor for its Oyster Creek Station in New Jersey, and this was a landmark moment because it was the first nuclear plant ordered on a purely economic basis, not subsidized by the government, not built as a demonstration project, but chosen because the utility believed it would generate cheaper electricity than a coal plant. General Electric offered the reactor as a turnkey project at a fixed price, essentially a loss leader to prove the technology could compete. And it worked, in the sense that it triggered a flood of orders. Between 1965 and 1967, American utilities ordered over 50 nuclear power plants. The industry called it the Great Bandwagon Market, and the name tells you something about the psychology. Everyone was jumping on. The plants being ordered in this period were much larger than Shippingport. We're talking about reactors in the range of 500 to over 1,000 megawatts of electrical output, enormous machines, among the largest and most complex engineering projects ever undertaken. Each one required years to build, thousands of workers, millions of components, and an extraordinary level of quality control. The reactor pressure vessel alone, That thick steel container that holds the nuclear core might weigh 500 tons and need to withstand pressures of over 150 atmospheres at temperatures above 300 degrees Celsius continuously for decades without a single significant flaw. Think about what that means from a metallurgical standpoint. You're asking a piece of steel to perform flawlessly under conditions that would destroy most materials, and you're asking it to do so for 30 or 40 years without replacement. The welds have to be perfect. The inspections have to be exhaustive. There is essentially no margin for error in the primary pressure boundary of a nuclear reactor, because if that boundary fails, you lose your coolant, and if you lose your coolant, you lose the ability to remove the decay heat that continues to be generated by the fuel even after the chain reaction has stopped. And that phrase, decay heat, is one of the most important concepts in all of nuclear engineering. Let me explain it, because it comes back again and again, and it's central to understanding every major nuclear accident that has ever occurred. When a nuclear reactor is operating, the fission chain reaction is producing the vast majority of the heat. But fission also creates hundreds of different radioactive isotopes, fission products, that are themselves unstable and continue to decay, releasing energy as they do. When you shut down the reactor, when you insert the control rods and stop the chain reaction, the fission stops almost immediately. But the fission products don't stop decaying. They can't. Their decay is governed by the laws of physics, and no control rod can change that. So even after shutdown, the fuel continues to generate heat. Right after shutdown, the decay heat is about 6 or 7% of the reactor's full operating power. That might not sound like much, but for a large reactor producing 3,000 megawatts of thermal power, 6% is 180 megawatts. That's an enormous amount of heat, enough to boil vast quantities of water very quickly. And if you can't remove that heat, if the cooling systems fail, the fuel temperature will rise, and eventually the fuel can be damaged. The cladding can fail, and in the worst case, the core can melt. This is the fundamental safety challenge of nuclear power, and it's worth sitting with for a moment. Unlike a coal plant or a gas turbine, which you can simply turn off and walk away from, a nuclear reactor demands continuous active cooling even after it's been shut down. The decay heat decreases over time. It drops to about 1% of full power within a few hours and continues to decline over days and weeks, but it never goes away entirely. For the first hours and days after shutdown, you absolutely must keep water flowing over the fuel. If you don't, the consequences can be catastrophic. In the entire history of nuclear safety engineering, every redundant pump and backup diesel generator and passive cooling system is fundamentally about solving this one problem, making sure that no matter what happens, earthquake, flood, loss of power, human error, equipment failure, you can always remove the decay heat. Now, through the 1960s, the engineers designing these plants were acutely aware of this challenge, and they built in multiple layers of protection. The concept is called defense in depth, and it's a beautiful piece of engineering philosophy. The idea is that you never rely on a single barrier or a single system. You stack multiple independent barriers between the radioactive fuel and the environment. First, the fuel itself is in the form of ceramic pellets, uranium dioxide, which can withstand extremely high temperatures and trap most fission products within their crystalline structure. Second, those pellets are sealed inside tubes of zirconium alloy cladding, which provides another containment barrier. Third, the entire reactor core is enclosed in that massive steel pressure vessel we talked about. Fourth, The pressure vessel and primary coolant system are enclosed inside a containment building, a huge structure typically made of reinforced concrete several feet thick, sometimes with a steel liner, designed to contain any radioactive release even if everything inside goes wrong. And then beyond that, you have emergency cooling systems, backup power supplies, and operational procedures, all designed to prevent things from reaching that point in the first place. It's an elegant, layered approach, and for the most part, it works remarkably well. The safety record of nuclear power, measured in deaths per unit of energy produced, is actually better than almost every other major energy source, including natural gas and even some renewables when you account for manufacturing and installation accidents. But the thing about nuclear accidents is that when they do happen, they're spectacular. They capture public attention in a way that a coal mine collapse or an oil refinery explosion never quite does, partly because of the invisible, lingering nature of radiation, and partly because of the deep psychological association between nuclear power and nuclear weapons. And it was the accidents, a handful of them, really, that would reshape the entire trajectory of the industry. The first major wake-up call came not from a power plant, but from a military reactor. In January 1961, at the National Reactor Testing Station in Idaho, the same sprawling desert facility where EBR-1 had made its 4 light bulbs glow a decade earlier, a small Army reactor called SL-1 suffered a catastrophic accident. SL-1 was a tiny thing, only about 3 megawatts thermal, designed as a portable power source for remote military installations. On the night of January 3rd, 3 operators were performing maintenance that required them to manually reconnect a control rod to its drive mechanism. What happened next is still not entirely understood, but somehow one of the operators withdrew the central control rod too far, too fast. The reactor went instantly supercritical, not just a controlled chain reaction, but a violent power excursion that vaporized water in the core so rapidly that the resulting steam explosion launched the entire reactor vessel upward, impaling one of the operators on the ceiling with a control rod. All 3 men died. They were the first people in history killed by a reactor accident in the United States. The SL-1 accident was horrifying, and the investigation that followed revealed troubling gaps in procedures and design. But it was a small, specialized military reactor, and the lessons, while important, didn't immediately shake public confidence in the growing civilian program. That confidence would hold for almost 2 more decades, through a period of massive expansion that saw nuclear power grow from a novelty to a major component of the electrical grid. By the mid-1970s, the United States had over 50 operating reactors and many more under construction. France was embarking on its own ambitious nuclear program. The Soviet Union was building reactors across Eastern Europe. Japan, Germany, Sweden, the United Kingdom. Country after country was betting on the atom. And then came the event that changed everything. On March 28, 1979, at a nuclear power plant on an island in the Susquehanna River in Pennsylvania, a series of mechanical failures, design flaws, and operator errors combined in a way that nobody had quite predicted. The plant was called 3 Mile Island, and the specific unit was TMI-2, a pressurized water reactor that had only been operating commercially for about 3 months. Brand new, essentially. And the sequence of events that unfolded that morning is one of the most studied, most analyzed chains of failure in the entire history of engineering, not because it killed people, because remarkably it didn't, but because it revealed just how badly things could go wrong even when every individual component was supposedly designed with safety in mind. Let's walk through it, because the details matter. They matter for understanding nuclear power, and they matter for understanding how complex systems fail in general. It started with something mundane. The secondary cooling loop. Remember, in a pressurized water reactor, you've got two loops. The primary one carrying intensely radioactive water through the core, and the secondary one where clean water gets turned to steam to spin the turbines. Well, sometime in the early morning hours, the pumps feeding water into the secondary side tripped off. The exact cause was probably a maintenance issue involving the condensate polishing system. Basically, the water purification equipment. Not dramatic, not exotic. A plumbing problem. But here's the thing about a nuclear power plant. Everything is connected to everything else. When the secondary pumps stopped, the steam generators couldn't remove heat from the primary loop anymore. The primary coolant started heating up. Pressure began to rise, and within seconds, exactly as designed, the reactor scrammed. All the control rods dropped into the core, and the fission chain reaction stopped cold. So far, the safety systems were doing their job perfectly. But remember what we talked about with decay heat? The chain reaction was over, but the fission products in those fuel rods were still decaying, still pumping out energy, something like 6 or 7% of full power right at the moment of shutdown. For a reactor producing around 900 megawatts of thermal energy, that's still over 50 megawatts of heat with nowhere to go. You need cooling. You absolutely, critically need cooling. Now, when the pressure in the primary loop rose past a certain point, a valve at the top of the pressurizer, a component that helps regulate pressure, opened automatically to release some of that pressure. This was also by design. The valve was called a pilot-operated relief valve, or PORV. It opened, steam vented out, and the pressure started coming down. Good. But then the pressure dropped to the point where the valve should have closed again, and here's where the first real problem hit. The valve stuck open. It didn't close. And the instrument in the control room that was supposed to tell the operators whether the valve was open or closed, it didn't actually measure the valve's position. It only showed whether the signal to close had been sent. The signal was sent. The light in the control room said the valve was closed. But it wasn't. Think about what that means. You've got a hole in the top of your primary cooling system, and nobody knows it's there. Superheated radioactive water and steam are pouring out through this stuck valve, draining the very coolant that's supposed to be keeping those fuel rods from overheating, and the operators are staring at an instrument panel that's telling them everything is fine with that valve. Meanwhile, the emergency core cooling system kicked in automatically, pumping water into the primary loop to make up for the falling pressure and water level. Again, exactly as designed. But the operators, looking at another instrument, the pressurizer level indicator, saw that the water level in the pressurizer was rising. And in their training, a rising pressurizer level meant the system was going solid, filling completely with water, which could cause its own set of dangerous pressure problems. So they did what their training told them to do. They throttled back the emergency cooling pumps. They reduced the flow of the very water that was keeping the core covered. And this is the heartbreaking part. They were making rational decisions based on what their instruments were telling them, but the instruments were painting a false picture. The pressurizer level was rising because the loss of coolant through that stuck valve was causing the remaining water in the system to flash into steam, and the steam was pushing water up into the pressurizer. The core itself was actually uncovering. The fuel rods were being exposed, with no water around them to carry away that relentless decay heat. For over 2 hours, this situation continued. The core temperature climbed. The zirconium cladding on the fuel rods, the same material chosen for its low neutron absorption, began reacting with the steam at high temperatures, producing hydrogen gas and more heat. The fuel rods warped, cracked, and eventually about half the core melted. Molten fuel slumped to the bottom of the reactor vessel. It was a partial meltdown, the thing that nuclear engineers had spent decades designing against. And yet, the containment held. That massive reinforced concrete structure surrounding the reactor vessel did its job. Some radioactive gases were released into the atmosphere, primarily xenon and krypton, and some radioactive water leaked into an auxiliary building. But the actual radiation exposure to the surrounding population was minimal. Studies later estimated an average additional dose of about 1 millirem to people living within a 10-mile radius, which is a fraction of what you'd get from a single chest X-ray. Nobody died. Nobody was even injured in any measurable way by radiation. But the damage to the nuclear industry was enormous, and in some ways permanent. The confusion during the accident, the conflicting information coming from the utility and from government agencies, the fact that for several days nobody was entirely sure whether a hydrogen bubble inside the reactor vessel might explode, all of it played out on live television. The movie The China Syndrome, about a nuclear accident, had been released just 12 days before TMI. The timing was almost unbelievable. Public trust, which had been quietly eroding through the 1970s as construction costs soared and environmental concerns grew, essentially collapsed overnight. In the United States, no new nuclear power plant was ordered after 1978 that wasn't eventually canceled. The Nuclear Regulatory Commission, which had replaced the old AEC in 1975 precisely because people recognized the conflict of interest in having the same agency both promote and regulate nuclear power, imposed sweeping new requirements. Control room design was overhauled. Operator training was transformed. The entire philosophy of how you think about reactor safety shifted from focusing on individual component reliability to thinking about the system as a whole, including the human beings operating it. TMI was, in a very real sense, the birth of what we now call human factors engineering in the nuclear industry. And the lessons extended far beyond nuclear power. The way TMI unfolded, small initial failure, misleading instruments, operators making logical decisions based on bad information, a cascade of errors compounding into catastrophe, became a template for understanding accidents in all complex systems. The sociologist Charles Perrow wrote a book called Normal Accidents, partly inspired by TMI, arguing that in sufficiently complex, tightly coupled systems, this kind of cascading failure isn't an anomaly. It's inevitable. It's normal. That's a sobering thought, and it applies to everything from chemical plants to air traffic control to financial markets. But the world didn't stop building nuclear plants after TMI. France, in particular, doubled down. The French had made a strategic decision in the early 1970s, after the oil crisis, to pursue energy independence through nuclear power, and they stuck with it. They standardized on a single PWR design, based, interestingly, on a Westinghouse license, and built reactor after reactor in a systematic, almost industrial fashion. By the late 1980s, France was generating over 70% of its electricity from nuclear power, a figure that still holds roughly true today. It's the most nuclear-dependent country on Earth, and the French experience is often held up as proof that nuclear power can be done efficiently and safely when you have political will, standardized designs, and a centralized decision-making structure. The Soviet Union, meanwhile, continued on its own path, building a very different kind of reactor. And this is where we need to talk about the RBMK, because understanding what made it different is essential for understanding what happened on April 26, 1986, in a city called Pripyat in northern Ukraine. The RBMK, the acronym is Russian, and it translates roughly to high-power channel type reactor, was a uniquely Soviet design. Unlike a PWR, which uses ordinary water as both coolant and moderator inside a massive steel pressure vessel, the RBMK used graphite as its moderator and water only as its coolant. The fuel channels ran vertically through a huge stack of graphite blocks, and the water flowed through individual pressure tubes surrounding each fuel channel rather than through one big vessel. This design had certain advantages from the Soviet perspective. You could build it big, over 1,000 megawatts, without needing the enormous pressure vessels that were difficult to manufacture. You could refuel it while it was still running, which improved its capacity factor. And you could use natural uranium or very low-enriched uranium as fuel, which was economically attractive. But the RBMK had a characteristic that Western reactor designers had deliberately avoided. It had what's called a positive void coefficient of reactivity under certain operating conditions. Now, let's unpack that, because it's absolutely critical. In a normal PWR, if the water in the core starts to boil and form steam bubbles, voids, those voids reduce the moderation of neutrons, which means fewer neutrons get slowed down to the right speed to cause fission, which means the chain reaction naturally decreases. The reactor has a built-in tendency to throttle itself down if it starts overheating. That's a negative void coefficient, and it's a beautiful, inherent safety feature. The RBMK, at low power levels, worked the opposite way, because the graphite was doing the moderating, not the water. When the water started boiling and forming voids, you lost some neutron absorption, but you didn't lose your moderator. The net effect was that more neutrons were available for fission. The reactor sped up. More power meant more boiling, which meant more voids, which meant even more power. A positive feedback loop, a reactor that, under the wrong conditions, would accelerate when you needed it to slow down. Soviet engineers knew about this characteristic. There were supposed to be operational procedures and safety systems to prevent operators from ever reaching the dangerous low-power regime where this positive void coefficient became dominant. But on the night of April 25, 1986, at Chernobyl Unit 4, a safety test was planned. Ironically, a test designed to improve safety by checking whether the turbine's residual spinning could provide enough electricity to run the emergency cooling pumps during a brief power outage. The test required the reactor to be at low power, and through a combination of schedule delays, operator inexperience, deliberate disabling of safety systems to prevent the test from being interrupted, and a fundamental misunderstanding of just how dangerous the reactor's physics became at low power with the particular configuration of control rods they were using, the operators maneuvered the reactor into exactly the state it should never have been in. When they initiated the test and the coolant flow decreased, the water began to boil. The positive void coefficient kicked in. Power surged. Someone hit the emergency shutdown button, the AZ5 button, which was supposed to drop all the control rods into the core. But the RBMK's control rods had a design flaw that reads almost like a cruel joke. The tips of the rods were made of graphite, a moderator, and when they first entered the core from the top, those graphite tips actually displaced water in the lower part of the channels, briefly increasing reactivity before the neutron-absorbing portion of the rods could take effect. In the state the reactor was in, that momentary increase was catastrophic. The power spike was almost instantaneous. Estimates suggest the reactor's thermal output surged to something like 100 times its normal maximum in a matter of seconds. The fuel itself shattered. Superheated steam pressure blew the 1,000-ton reactor lid, a massive biological shield they called the Elena, clean off the top of the reactor. It landed back down at an angle. A second explosion followed almost immediately, likely a steam explosion or possibly a hydrogen explosion, though the exact nature of that second blast is still debated by physicists. This one blew the roof off the reactor building entirely, exposing the burning graphite core directly to the open night sky. And here's what made Chernobyl fundamentally different from 3 Mile Island. At TMI, the containment held. The concrete and steel dome did exactly what it was designed to do. It kept the radioactive material inside. The RBMK reactor at Chernobyl had no such containment structure. It was too large, too spread out. The reactor building itself was just an industrial building, not a pressure-rated containment vessel. So when that roof blew open, there was nothing between a burning nuclear reactor core and the atmosphere. Burning chunks of graphite and reactor fuel were scattered across the roof of the adjacent Unit 3 building and the grounds around the plant. The graphite fire burned for days, sending a plume of radioactive material, cesium-137, iodine-131, strontium-90, plutonium isotopes, high into the atmosphere where winds carried it across Belarus, Ukraine, Scandinavia, and eventually, in detectable traces, across most of Europe. The human cost began immediately. The plant workers and firefighters who responded that night were exposed to staggering doses of radiation. Many of them didn't fully understand what they were dealing with. The firefighters climbed onto the roof of the turbine hall to put out fires, picking up pieces of graphite with their hands. 28 of the emergency responders and plant workers died within months from acute radiation syndrome. Their bravery was extraordinary, and their suffering was terrible, and it deserves to be stated plainly, without dramatization. They walked into conditions that were, in the most literal sense, unsurvivable, and many of them knew something was deeply wrong even as they kept working. The evacuation of Pripyat, the nearby city of about 50,000 people built specifically to house Chernobyl's workers, didn't begin until 36 hours after the explosion. The delay was partly due to the slow flow of accurate information up the Soviet chain of command, partly due to political reluctance to acknowledge the scale of the disaster. Eventually, a massive exclusion zone was established, 30 kilometers in radius, and over 100,000 people were permanently relocated. The long-term health effects, particularly thyroid cancer in children exposed to iodine-131, have been documented extensively, though the total attributable death toll remains a subject of genuine scientific debate, with estimates ranging from a few thousand to tens of thousands of excess cancer deaths over decades, depending on the methodology and assumptions used. But let's talk about what Chernobyl meant for nuclear power as a technology and as an idea. Because the consequences rippled outward in ways that are still shaping the world you live in today. The most immediate effect was psychological and political. If 3 Mile Island had wounded public confidence in nuclear energy, Chernobyl nearly killed it. The images, the destroyed reactor building, the ghost city of Pripyat, the hazmat suits, the concrete sarcophagus hastily built over the ruined core, became the defining visual vocabulary of nuclear fear. It didn't matter that the RBMK was a uniquely flawed Soviet design with no real equivalent in the West. It didn't matter that Western reactors had containment structures specifically designed to prevent this kind of release. In the public imagination, nuclear was nuclear. A reactor was a reactor, and reactors could do this. Country after country pulled back. Italy held a referendum in 1987 and voted to shut down its nuclear plants. Sweden committed to a phase-out. Austria, which had actually built a nuclear plant at Zwentendorf, but never operated it after a 1978 referendum, felt thoroughly vindicated. Germany's anti-nuclear movement, already strong, gained unstoppable momentum that would eventually lead to the Atomausstieg, the nuclear exit, decades later. In the United States, where no new nuclear plants had been ordered since before TM11 anyway, Chernobyl sealed the coffin. The technology that had once promised electricity too cheap to meter was now, in the minds of millions, simply too dangerous to tolerate. And yet, France kept its reactors running. Japan kept building. South Korea kept building. The global installed nuclear capacity actually continued to grow through the late 1980s and into the 1990s because plants that had been ordered and started years earlier were still being completed. But the pipeline of new orders had dried up almost everywhere. Nuclear power entered a long, strange middle age. The existing fleet kept generating enormous amounts of electricity, reliably and with remarkably low carbon emissions, but almost nobody wanted to build new ones. Now, here's something worth sitting with for a moment, because it connects to everything we've been talking about. The engineering lessons from both TMI and Chernobyl were actually learned. They were incorporated. The global nuclear industry created organizations like the World Association of Nuclear Operators, WANO, specifically to share operational experience and safety practices across borders, because Chernobyl had proven that a nuclear accident anywhere was a nuclear accident everywhere. Reactor designs were scrutinized and improved. The positive void coefficient issue in remaining RBMKs was addressed through modifications. Human factors engineering, the field that barely existed before TMI, became central to reactor operations worldwide. Probabilistic risk assessment grew more sophisticated. Defense in depth got deeper. The fleet of reactors that kept running through the 1990s and 2000s compiled a safety record that was, by any objective measure, extraordinary. Capacity factors, the percentage of time a reactor actually generates power compared to its theoretical maximum, climbed from around 60% in the 1970s to over 90% by the 2000s in the United States. These plants were running better, more safely, and more efficiently than ever. The people operating them were better trained, better supported by technology, and working within a safety culture that had been forged in the fires of real disasters. But public perception and political will don't always track with engineering reality. And the economics had shifted too. Natural gas was cheap, especially in the United States after the shale revolution began in earnest in the mid-2000s. Wind and solar costs were starting their dramatic decline, and building new nuclear plants had become extraordinarily expensive and slow, partly because of genuinely necessary safety requirements, and partly because the industry had lost the institutional knowledge and supply chain capacity that comes from actually building things regularly. France had built dozens of standardized plants in the 1970s and 80s because they kept building. The workforce learned, the supply chain matured, costs came down. When you stop building for 20 years and then try to start again, you're essentially starting from scratch. And it shows. Which brings us to March 11th, 2011, the Tohoku earthquake off the northeast coast of Japan. Magnitude 9.0, one of the most powerful earthquakes ever recorded. The earthquake itself was handled remarkably well by Japan's nuclear fleet. Reactors detected the seismic activity and scrammed automatically. Control rods inserted. Fission stopped, just as designed. The plants along the coast withstood the shaking. But remember that concept we talked about earlier. Decay heat? The fission products in the fuel don't care that you've shut down the chain reaction. They keep decaying, keep generating heat, and you need cooling water circulating to carry that heat away. For hours, for days, the earthquake knocked out the external power grid. That's what the backup diesel generators were for. At the Fukushima Daiichi plant, operated by Tokyo Electric Power Company, TEPCO, those generators started up and began powering the cooling systems. Everything was working. And then, roughly 45 minutes after the earthquake, the tsunami arrived. The waves that hit Fukushima Daiichi were estimated at 14 to 15 meters high. The plant's seawall was designed for waves of about 5.5 meters. The tsunami overwhelmed the seawall, flooded the low-lying areas where the backup diesel generators were housed, and destroyed them. It also knocked out the electrical switching equipment. The plant lost all AC power. Some units still had battery backup, direct current, but batteries don't last forever. When they ran out, the operators had no way to pump cooling water through the reactors. And now you're in the nightmare scenario that every nuclear engineer understands in their bones. You have reactors full of intensely hot fuel, decay heat building with no way to remove it, and the clock is ticking. Over the next several days, 3 of the 6 reactor units at Fukushima Daiichi suffered core meltdowns. Hydrogen gas, generated when the overheated zirconium fuel cladding reacted with steam, accumulated in the reactor buildings and exploded. Not nuclear explosions, but hydrogen detonations that blew apart the upper structures of the buildings in dramatic, terrifying blasts captured on live television and broadcast worldwide. Radioactive material was released. Over 100,000 people were evacuated from the surrounding area. The Japanese government established an exclusion zone, and once again, the world watched a nuclear disaster unfold in real time. But here's where Fukushima's story diverges from Chernobyl's in ways that are important and often overlooked. The radiation released from Fukushima was roughly 1/10 of what Chernobyl released. Some estimates say less. The containment structures, though damaged, did limit the release significantly compared to an open, burning core. And the direct health effects from radiation exposure have been, according to the United Nations Scientific Committee on the Effects of Atomic Radiation, minimal. No deaths have been directly attributed to radiation from the Fukushima accident. The health consequences were real, but came primarily from the stress, disruption, and trauma of the evacuation itself, particularly among elderly residents. This is not to minimize the disaster. It was devastating. The economic costs were staggering. The environmental contamination was real and required years of painstaking cleanup that continues today. But the engineering performed differently than the public narrative often suggests. The political consequences, though, were immediate and severe. Germany, under Chancellor Angela Merkel, herself a physicist who understood the technology, reversed course and committed to shutting down all of its nuclear plants, a process completed in April 2023. Japan shut down its entire nuclear fleet for safety reviews, and the restart process has been agonizingly slow, with only a fraction of its reactors back online more than a decade later. The global narrative of nuclear decline seemed confirmed. And yet, something strange started happening in the years after Fukushima. Something that Alvin Weinberg, that quiet visionary from Oak Ridge who'd been arguing for decades about the importance of nuclear safety and the potential of alternative reactor designs, might have appreciated even though he didn't live to see it. He passed away in 2006. The conversation about nuclear power began to shift, slowly at first, then with gathering momentum, driven by a force that hadn't been part of the nuclear debate in any serious way before: climate change. Because as the world began grappling with the sheer scale of decarbonization required to avoid the worst outcomes of global warming, people started looking at the numbers. And the numbers told an interesting story. Nuclear power, for all its political baggage, for all its spectacular and traumatic failures, remained one of the largest sources of carbon-free electricity on the planet. In the early 2020s, nuclear generated roughly 10% of the world's electricity, and in the countries that relied on it heavily, France, with its fleet still humming along, or Sweden, or several others, it provided a baseload of clean power that no other source could easily replace. And that's the thing that started to dawn on people, not just environmentalists, not just engineers, but policymakers, economists, even some of the activists who'd spent their careers opposing nuclear energy. When you look at what it actually takes to decarbonize an entire electrical grid, the math gets humbling very quickly. Think about it this way. A single large nuclear plant, say, a typical pressurized water reactor producing about a gigawatt of electrical power, runs at capacity factors above 90%, as we talked about earlier. That means it's churning out electricity almost all the time, day and night, rain or shine, summer and winter. To replace that output with wind turbines, you'd need something like 300 or more large turbines spread across a vast area, and even then, you'd need some form of energy storage or backup for the times when the wind isn't blowing. Solar has a similar challenge. It's fantastic during sunny afternoons, but it produces nothing at night, and much less on cloudy days. None of this means wind and solar aren't essential. They absolutely are, and their growth has been one of the great engineering success stories of the 21st century. But the question that kept nagging at serious energy analysts was this: can you build a fully decarbonized grid using only intermittent renewables and storage at the scale and speed the climate crisis demands? And for a lot of people who ran the numbers honestly, the answer came back. It's going to be extraordinarily difficult without firm, dispatchable, carbon-free power. And nuclear is the most proven technology that fits that description. This realization didn't arrive as a thunderclap. It crept in. You could see it in the language of reports from the Intergovernmental Panel on Climate Change, the IPCC, which in its various assessment reports and special publications consistently included nuclear power in most of its modeled pathways to limiting warming to 1.5 or 2 degrees Celsius. You could see it in the shifting positions of environmental organizations, some of which began softening their opposition, or at least acknowledging that existing nuclear plants shouldn't be shut down prematurely if the alternative was burning more natural gas. James Hansen, the NASA climate scientist who'd done more than almost anyone to bring global warming to public attention, became an outspoken advocate for nuclear power, arguing that opposing it in the name of environmentalism was, in his view, a tragic misunderstanding of the scale of the problem. And then there were the real-world demonstrations. When you compared countries that had invested heavily in nuclear with countries that hadn't, the carbon intensity of their electricity told a stark story. France, generating roughly 70% of its power from nuclear, had some of the cleanest electricity in Europe. Its grid emissions were a fraction of Germany's, which had spent hundreds of billions of euros on its Energiewende, its energy transition, but had replaced its nuclear output largely with renewables and natural gas, and sometimes even coal when the wind wasn't cooperating. By the early 2020s, Germany's electricity sector carbon emissions per kilowatt hour were often several times higher than France's. That comparison became a kind of Exhibit A in the pro-nuclear argument, and it was hard to argue with the data. But here's the thing, and this is where the story gets really interesting for the future. Even as the case for nuclear power strengthened on climate grounds, the old problems hadn't gone away. Building large conventional nuclear plants in Western countries had become almost prohibitively expensive and slow. The poster children for this problem were two projects that became infamous in the industry. In Finland, the Olkiluoto 3 reactor, a European pressurized reactor, or EPR, built by the French company Areva, broke ground in 2005 with an estimated cost of about 3 billion euros and a completion date around 2009. It finally began regular commercial operation in April 2023, roughly 14 years late, at a cost that ballooned to somewhere around 11 billion euros. In the United States, the Vogtle expansion in Georgia told a similar story. Two new AP1000 reactors, designed by Westinghouse, were approved in 2012 with an estimated cost of about $14 billion. By the time Unit 4 entered commercial service in early 2024, the total cost had swelled to around $35 billion, and the project was years behind schedule. The original contractor, Westinghouse, had gone bankrupt in 2017, partly because of losses on this and a similar project in South Carolina that was abandoned entirely after spending $9 billion. These weren't just numbers on a spreadsheet. They represented a genuine crisis for the nuclear industry. Because even if you could make the case that nuclear was essential for the climate, you had to be able to build it at a reasonable cost and in a reasonable time frame, or it simply couldn't scale fast enough to matter. And the reasons for these overruns were complex. Decades of atrophied construction expertise, a workforce that had largely dispersed since the last building boom, first-of-a-kind engineering challenges with new reactor designs, regulatory processes that were thorough but sometimes painfully slow, and supply chains that had to be rebuilt almost from scratch. It turned out that building nuclear plants is one of those things where you get better with practice, and the West had essentially stopped practicing. Which brings us to what might be the most consequential development in nuclear energy in the early 21st century: the emergence of new reactor designs and new approaches to building them. And this is where Alvin Weinberg's ghost really does seem to hover over the story, because some of these designs draw directly on ideas he championed at Oak Ridge decades ago. Let's talk about small modular reactors first, SMRs, as the industry calls them. The concept is deceptively simple. Instead of building enormous bespoke plants on site, which is where so much of the cost and schedule risk comes from, you design a smaller reactor, maybe 77 megawatts or 300 megawatts instead of 1,000 or more, and you build as much of it as possible in a factory. Then you ship the modules to the site and assemble them. The idea is to capture the economies of mass manufacturing rather than the economies of scale that drove the industry toward ever larger plants in the 1960s and 70s. Think about it like the difference between building a custom mansion on site, with every beam cut to order, versus building modular homes in a factory where you can control quality, train workers on repetitive tasks, and learn from each unit you produce. NuScale Power, based in Oregon, became the first SMR design to receive approval from the U.S. Nuclear Regulatory Commission in 2020 for its 77-megawatt light water module. The design was elegant in its safety philosophy. The reactor vessel sat inside a containment vessel, both submerged in a large pool of water, and the whole system relied on natural circulation and passive cooling. No pumps needed to keep the core cool during a shutdown. Gravity and convection did the work. It was, in a sense, the logical endpoint of the post-TMI, post-Fukushima safety evolution. Design the reactor so that even if every operator walks away and every backup system fails, physics itself prevents a meltdown. However, NuScale's first planned project, at the Idaho National Laboratory, was canceled in late 2023 when the estimated costs rose to the point where the participating utilities pulled out. The technology worked, but the economics, at least for that first project, didn't close. And that tension between technical promise and economic reality remains the central drama of the nuclear industry's attempted comeback. But SMRs are only part of the story. There's a whole zoo of advanced reactor concepts in various stages of development, and some of them represent genuinely different approaches to nuclear fission. Molten salt reactors, for instance, the very concept that Weinberg's team demonstrated at Oak Ridge in the 1960s with the molten salt reactor experiment. In these designs, the nuclear fuel is dissolved directly in a molten salt mixture, which serves as both the fuel carrier and the coolant. The salt operates at high temperatures but low pressures, which means you don't need the massive, thick-walled pressure vessels that conventional reactors require. If the system overheats, a freeze plug at the bottom melts and the fuel drains by gravity into a passively cooled tank. It's an inherently walk-away safe concept. Several companies, Terrestrial Energy in Canada, Kairos Power in the United States, and others, are pursuing variations on this theme. Then there are high-temperature gas-cooled reactors, which use helium as a coolant and can operate at temperatures high enough to provide industrial process heat, something that matters enormously for decarbonizing sectors like cement, steel, and chemical manufacturing, which can't easily be electrified. There are fast neutron reactors that can, in principle, burn spent fuel from conventional reactors, dramatically reducing the volume and longevity of nuclear waste, addressing one of the public's deepest and most legitimate concerns. And there are even microreactors, tiny units producing just a few megawatts, designed for remote communities, military bases, or disaster relief. Now, you might be thinking, this all sounds wonderful on paper, but haven't we heard promises about advanced reactors before? And you'd be right to be skeptical. The history of nuclear energy is littered with concepts that worked beautifully in theory, but stumbled in practice. The key difference in the 2020s, though, is the convergence of several forces that hadn't aligned before. The climate imperative is real and growing more urgent with every passing year. Government funding has returned. The U.S. Department of Energy has invested billions in advanced reactor demonstrations, and the 2022 Inflation Reduction Act included production tax credits for nuclear power for the first time, putting it on equal footing with wind and solar. Private capital has flooded in too, with billions in venture funding going to nuclear startups, and perhaps most importantly, there's a new source of demand that nobody saw coming even a few years ago: artificial intelligence. The explosion of AI and large language models in the early 2020s created an enormous and rapidly growing appetite for electricity to power data centers. Tech companies like Microsoft, Google, and Amazon, all of which had made ambitious carbon neutrality commitments, found themselves needing vast amounts of reliable, carbon-free power, available 24 hours a day, 7 days a week. And that description fits nuclear perfectly. In 2024, Microsoft signed a deal to purchase power from the restarted 3 Mile Island Unit 1, not the damaged Unit 2, but its sister reactor, which had operated safely for decades before being shut down for economic reasons in 2019. The symbolism was almost too perfect. 3 Mile Island, the name synonymous with nuclear fear, becoming a symbol of nuclear's potential rebirth, powered by the demands of artificial intelligence. You couldn't make it up. China, meanwhile, has been doing something that the rest of the world has largely failed to do: actually building nuclear plants on time and on budget, at scale. By the mid-2020s, China had the world's largest pipeline of reactors under construction, with plans that could see its nuclear fleet surpass both France's and America's. The Chinese approach benefited from exactly what Western projects lacked: continuous construction experience, a deep workforce, standardized designs built repeatedly, and a regulatory environment that, for better or worse, could move faster. Whether China's nuclear expansion will be the model for the rest of the world, or whether it reflects unique conditions that can't be replicated in democracies with more complex regulatory and social dynamics, is one of the great open questions of energy policy. And then there's the question that has shadowed nuclear power from the very beginning, the question that no amount of engineering brilliance has fully answered. What do you do with the waste? Spent nuclear fuel remains radioactive for thousands of years, some isotopes for hundreds of thousands. Every country that operates nuclear plants has accumulated spent fuel, most of it sitting in cooling pools and dry cask storage at reactor sites, waiting for a permanent solution. Finland, remarkably, has actually built one. The Onkalo repository, carved deep into ancient bedrock on the island of Olkiluoto, is designed to isolate spent fuel for at least 100,000 years. It's expected to begin accepting waste in the mid-2020s, making Finland the first country in the world to have a functioning deep geological repository. Sweden is close behind. The United States, famously, spent decades and billions of dollars developing the Yucca Mountain Repository in Nevada before it was effectively killed by political opposition. The waste remains scattered across dozens of sites around the country. It's a solvable engineering problem. The geology is well understood, the containment technology exists, but it's a political problem that has proven far harder to crack. So here we are. More than 80 years after Enrico Fermi's team pulled those cadmium control rods from a pile of graphite and uranium in a squash court beneath the University of Chicago, nuclear power sits at one of the most fascinating crossroads in its long and turbulent history. It is simultaneously one of the oldest and newest forms of energy technology. The basic physics, neutrons splitting heavy atoms, releasing energy, sustaining a chain reaction, hasn't changed since that December afternoon in 1942. But everything around it has. The materials, the safety systems, the digital controls, the fuel forms, the regulatory frameworks, the economics, the politics, and above all, the context. The world that nuclear power now operates in is a world facing a climate emergency, an energy security crisis, and an insatiable demand for clean electricity. And in that world, the technology that once seemed destined for obsolescence has found new relevance. Whether this nuclear moment turns into a genuine renaissance or fades into another cycle of hype and disappointment depends on questions that haven't been answered yet. Can the new reactor designs actually be built affordably? Can the supply chains be rebuilt? Can public trust be earned, not through slogans, but through demonstrated safety and transparency? Can the waste problem be solved politically, not just technically? These are hard questions, and honest people disagree about the answers. But what's undeniable, as you lie here thinking about it, is the sheer improbability and beauty of the whole story. That it starts with a Greek philosopher wondering whether matter could be divided forever, that it passes through a woman in a Swedish forest working out the physics of a barium puzzle on a scrap of paper in the snow, that it includes a reactor built under a football stadium, a submarine that sailed under the North Pole, a city abandoned overnight, and a wave that crossed an ocean to reshape energy policy on the other side of the world. It's a story about atoms, yes, But really it's a story about people. Curious, stubborn, brilliant, flawed people trying to understand the universe and then trying to use that understanding to power civilization. And that story isn't over. It's still being written by engineers and physicists and policymakers and ordinary citizens right now, tonight, while you drift off to sleep. The atoms are still there, still holding their enormous energy, patient and quiet, waiting to see what we decide to do next.